Picture this. You're standing in a cave in Ethiopia, holding a 3.2 million-year-old skeleton in your hands. Her name is Lucy, and she's looking back at you across an almost incomprehensible gulf of time. But here's what will blow your mind. Between her time and ours, our species has survived ice ages, volcanic winters, and mass extinctions. We've watched entire mountain ranges rise and fall. We've shared the planet with giants, saber-toothed cats, and woolly mammoths. Yet somehow, impossibly, the genetic thread connecting you to Lucy has never been broken. But Lucy isn't the beginning of our story. She's just one chapter in an epic that spans 7 million years. A tale of survival against odds so impossible that it reads like science fiction. Our ancestors didn't just survive. They thrived in landscapes so alien they might as well have been on another planet. They developed tools when they barely had brains larger than chimpanzees. They controlled fire before they could even speak. They created art before they invented agriculture. And here's the most mind-bending part. We're still evolving. Right. Now, as you're reading this, your DNA carries the genetic signatures of at least 3 different human species. You're not just Homo sapiens, you're a walking, breathing mixture of ancient love stories between our ancestors and mysterious relatives, whose names we're only now learning to pronounce. Neanderthals, DENISOVANS, and others lost to time. So how did we get here? How did a small group of African apes become the dominant species on Earth? The answer will change everything you thought you knew about being human. Chapter 1. When we stopped being apes 7 million years ago, in the heart of what we now call Africa, something extraordinary happened. In the dense forests that stretched across the continent like a green ocean, a group of apes made a choice that would echo through millennia. They looked beyond the safety of the trees and stepped down into an uncertain world below. This wasn't a sudden decision. Evolution never works that way. Instead, it was a gradual awakening, spread across hundreds of thousands of years. These early ancestors, caught between 2 worlds, began to change in ways that would seem impossible to their tree-dwelling cousins. Their spines straightened. Their legs grew longer. Their hands, freed from the constant grip of branches, began to explore new possibilities. The timeline of human evolution began some 4 billion years ago, but the critical branching of the human lineage from the one that produced great apes occurred in Africa sometime between 6 and 7 million years ago. This moment, this great divergence, marked the beginning of a journey that would take our ancestors from the forests of Africa to every corner of the earth. But what drove this momentous change? Why did some apes choose the ground while others remained in the trees? The story begins with climate. Each and every species of early hominin was successfully adapted to its lifestyle and was not evolving toward any end. There's no predetermined direction in the evolution of species. Natural selection hones them. Natural selection hones them. Around 7 million years ago, Africa was experiencing massive environmental shifts. The supercontinent was literally tearing itself apart as the Great Rift Valley formed, creating new landscapes and fragmenting the once continuous forests. As forests shrank and grasslands expanded, our ancestors found themselves at a crossroads. They could retreat deeper into the remaining forests, or they could adapt to this new open world. Some chose adaptation, and in doing so, they began the long journey toward humanity. The earliest evidence of this transition comes from species like Sahelanthropus chidensis, discovered in Chad and nicknamed Tumai. Identifying the earliest member of the human tribe, Hominini, is difficult because the predecessors of modern humans become increasingly ape-like as the fossil record is followed back through time. Living about 7 million years ago, Tumai represents one of our earliest known ancestors. Though the evidence is tantalizingly incomplete, just a single skull, some jaw fragments, and teeth. What makes Tamai significant isn't just his age, but his anatomy. His face projects forward less than that of modern apes, and his canine teeth are smaller, both early hints of the changes that would define our lineage. But perhaps most intriguingly, the position of the foramen magnum, the hole where the spine connects to the skull, suggests he may have walked upright at least some of the time. This brings us to one of the most revolutionary developments in our evolutionary history: bipedalism. Walking on two legs wasn't just a change in how our ancestors moved. It was a complete reimagining of what it meant to be a primate. The ability to walk upright may have offered survival benefits, such as the ability to spot dangerous predators earlier. Perhaps crucially, it left the hands free to do other tasks, such as carry food and use tools. But why did bipedalism evolve? The savanna hypothesis suggests that as forests gave way to grasslands, our ancestors needed to travel longer distances between scattered groves of trees. Walking upright was more energy efficient for long-distance travel than the knuckle walking used by chimpanzees and gorillas. Standing tall also provided a crucial advantage: the ability to see over tall grass to spot both predators and prey. Yet, recent discoveries have complicated this simple narrative. Bipedalism appears to have been established in the 6-million-year-old Ororhyntuganensis, a pre-Australopithecus found in the Tugan Hills near Lake Baringo in central Kenya. Ororhyn, whose name means original man in the local Tugan language, lived in a mixed environment of forests and grasslands, suggesting that bipedalism may have evolved before the full transition to savanna life. The evidence from Ororhyn comes primarily from femur bones that show adaptations for upright walking. The femur head is large relative to the shaft, and the femur neck is long, both features that would have supported the body's weight during bipedal locomotion. Even more compelling, the fossil shows evidence of what scientists call cortical remodeling, the thickening of bone in response to the stresses of upright walking. Meanwhile, another early human ancestor was making its mark in Ethiopia. Ardipithecus ramidus, or Ardi, lived about 4.4 million years ago in an environment very different from the Africa we know today. Two species of Ardipithecus from Ethiopia have reduced canines and a bowl-shaped pelvis that indicates an upright posture. Rather than the dry savannas we might expect, Ardi's world was a mosaic of woodlands, forests, and grasslands. Ardi represents a fascinating transitional form. Her pelvis shows clear adaptations for bipedalism, but her hands and feet retain features that would have made her an excellent climber. She could walk upright on the ground and scramble through trees with equal facility, a dual lifestyle that modern humans have completely lost. But perhaps most remarkably, Ardi's social structure may have been fundamentally different from that of modern apes. The species was first described in 1995 after an analysis of isolated teeth, upper and lower jaws, fragments of a cranium, and a tibia unearthed at the discovery sites. Unlike chimpanzees and gorillas, where males are significantly larger than females, Ardi's species shows much less sexual dimorphism. This suggests a more cooperative social structure, possibly with reduced competition between males and more pair bonding between males and females. This social evolution may have been just as important as physical changes. As our ancestors adapted to life on the ground, they would have faced new challenges: longer migrations between food sources, increased exposure to predators, and the need for more complex coordination between group members. The development of stronger social bonds and more sophisticated communication would have been crucial for survival. This great divergence set the stage for everything that followed in human evolution. By committing to life on two legs, our earliest ancestors embarked on a path that would lead to larger brains, sophisticated tools, and eventually global colonization. But the transition wasn't sudden or simple. It was a gradual process that took millions of years and involved countless species, most of which we're only now discovering. The fossil record from this period is frustratingly incomplete, leaving us with tantalizing glimpses of our earliest ancestors rather than a complete picture. Each new discovery, whether it's a skull fragment from Chad or a femur bone from Kenya, adds another piece to an enormous puzzle that spans continents and millions of years. What's becoming clear is that the early stages of human evolution were characterized by diversity rather than a single linear progression. Multiple species of early hominins lived alongside each other, experimenting with different approaches to bipedalism, different social structures, and different survival strategies. Some succeeded and gave rise to later species. Others became evolutionary dead ends. This diversity would become a hallmark of human evolution, and it sets the stage for our next chapter, the rise of the Australopiths, the southern apes, who would perfect the art of upright walking and lay the groundwork for the emergence of our own genus, Homo. As these early pioneers established themselves as ground-dwelling bipeds, they were setting in motion changes that would reshape not just their bodies, but their entire way of life. The descendants of these first upright apes would spread across Africa, diversifying into dozens of species over the next several million years. Among them would emerge a group that would become some of the most successful and long-lived human ancestors in our family tree, the Australopiths. Their story begins about 4.2 million years ago with a species whose fossils would revolutionize our understanding of human evolution and whose most famous representative would become the most beloved ancestor in the world. Chapter 2: Masters of the African Landscape. On November 24, 1974. In the baking heat of the Afar Triangle in Ethiopia, a young graduate student named Tom Gray was walking alongside his advisor, Donald Johansson, when something caught his eye. Protruding from the ancient sediment was what looked like a piece of arm bone. As they began to excavate, they realized they were looking at something extraordinary, the most complete early human skeleton ever discovered. That night, as Lucy in the Sky with Diamonds played on the camp radio, they named their find Lucy, a 3.2 million-year-old woman who would become the most famous human ancestor in the world. But Lucy wasn't just a single individual. She represented an entire group of human ancestors called the Australopiths, whose story spans over 2 million years, and whose success would pave the way for our own genus. Australopithecus afarensis is one of the longest-lived and best-known early human species. Paleoanthropologists have uncovered remains from more than 300 individuals. The Australopiths weren't just evolutionary stepping stones. They were masters of the African landscape, perfectly adapted to their world and successful in ways that would make modern humans envious. The Australopiths, whose name literally means southern apes, represent one of the most successful adaptive radiations in human evolutionary history. Australopithecus represents a successful adaptive radiation of hominins that persisted for more than 2 million years of time, perhaps even longer than our genus, Homo, has done so far. These weren't primitive transitional forms shambling toward humanity. They were sophisticated, successful species perfectly adapted to their environments. The story begins around 4.2 million years ago with Australopithecus anamensis, the earliest confirmed member of the genus. The earliest member of the genus Australopithecus is O. anamensis, which was discovered in northern Kenya near Lake Turkana at Kanapoi and Alia Bay. Found in the fossil-rich sediments around Lake Turkana, O. anamensis shows clear evidence of bipedal locomotion while retaining many primitive features that linked it to earlier species like Ardipithecus. What sets O. anamensis apart is its teeth. The teeth of thick enamel, like the teeth of all later hominins, but unlike those of Arametus, which have ape-like thin enamel. This thick enamel suggests a significant dietary shift. These early Australopiths were processing tougher, more abrasive foods than their forest-dwelling ancestors. They were adapting to a world where fruits and soft leaves were less abundant, and harder seeds, nuts, and tubers were becoming dietary staples. The fossil evidence from O. annamensis also provides compelling proof of bipedalism. The tibia shin bone exhibits anatomy at both the knee and ankle ends characteristic of later bipedal hominins. The knee joint shows adaptations for weight-bearing during upright walking, while the ankle reveals the development of a more rigid foot structure necessary for efficient bipedal locomotion. By 3.9 million years ago, O. annamensis had evolved into or been replaced by Australopithecus afarensis lucy species, found between 3.85 and 2.95 million years ago in eastern Africa, Ethiopia, Kenya, Tanzania. This species survived for more than 900,000 years, which is over 4 times as long as our own species has been around. The longevity of O. afarensis is truly remarkable when you consider that modern humans have only been around for about 300,000 years. Lucy herself provides an incredible window into the world of these ancient human ancestors. Standing just over 3 feet tall and weighing perhaps 60 pounds, she was fully grown when she died around 3.2 million years ago. Because she could walk upright on the ground and climb trees, she and other members of her species were able to use resources from woodlands, grasslands, and other diverse environments. This versatility was key to their success. They weren't locked into a single ecological niche, but could exploit multiple environments as conditions changed. The anatomy of O. afarensis reveals fascinating insights into their lifestyle. Their brains were still quite small, roughly 400 to 500 cubic centimeters, about the size of a chimpanzee's brain. But their bodies were becoming increasingly human-like in proportions. Their canines were smaller, like modern humans, and with the teeth less interlocked than in previous hominins. In fact, in some Australopithecines, the canines are shaped more like incisors. This reduction in canine size is particularly significant because large, projecting canines are typically associated with male competition and aggression in primates. The smaller canines of Australopiths suggest reduced sexual dimorphism and perhaps a more cooperative social structure. However, body size differences between males and females were still pronounced. In modern populations, males are on average a mere 15% larger than females, while in Australopithecus, males could be up to 50% larger than females by some estimates. Perhaps the most compelling evidence for Australopith behavior comes not from fossils, but from footprints. At Latoli in Tanzania, Mary Leakey's team discovered something extraordinary: a trackway of footprints preserved in volcanic ash dating to 3.6 million years ago. These footprints, made by at least 3 individuals, show clear evidence of upright walking. The prints reveal a stride length and foot anatomy remarkably similar to modern humans, though with some key differences that reflect their transitional nature. The Latoli footprints tell a story that goes beyond anatomy. They capture a moment in time. 2 adults and possibly a child walked across the landscape, their feet sinking into freshly deposited volcanic ash that would harden and preserve their passage for millions of years. Some researchers have even suggested that the smaller prints show evidence of playful behavior, with the individual occasionally stepping in the footprints of one of the adults. But the Australopiths weren't a single, uniform group. As the climate continued to change and new ecological niches opened up, they diversified into multiple species with different adaptive strategies. Around 3.3 million years ago, in the same region where O. afarensis lived, a different species was making its own mark on the landscape. In 2015, a team under Johannes Heil Selassie described in the journal Nature a new species, a Deiramida, from the Afar language. Dei meaning close and Ramida meaning relative. Australopithecus deiramida shows that the path of human evolution was far from linear. If correct, Afarensis was not the only hominin around in East Africa at this time. Multiple species of Australopiths lived alongside each other, possibly occupying different ecological niches or different regions within the same landscape. This pattern of diversity would become a recurring theme throughout human evolution. Meanwhile, in South Africa, a different lineage of Australopiths was evolving. Australopithecus africanus, the first Australopith ever discovered, lived between 3.3 and 2.1 million years ago. The specimen was studied by the Australian anatomist Raymond Dart, who was then working at the University of the Witwatersrand in Johannesburg. The fossil skull was from a 3-year-old bipedal primate, nicknamed Tongchild, that he named Australopithecus african.o. Africanus represents a fascinating evolutionary experiment. Living in the more varied landscapes of southern Africa, they developed slightly different adaptations than their eastern cousins. Their brains were marginally larger, their faces slightly less projecting, and their teeth showed adaptations for processing a more varied diet. The success of the Australopiths extended beyond just physical adaptations. Evidence suggests they were capable of using simple tools, though they probably didn't manufacture them in the way later human species would. Scratches on bones found near Australopith sites suggest they may have used stones to break open bones for marrow, and wear patterns on their teeth indicate they may have used their teeth as tools for processing plant materials. The Australopiths represent a crucial chapter in human evolution, one that demonstrates the power of adaptive flexibility. Rather than being locked into a single ecological niche, they exploited multiple environments and developed diverse survival strategies. Their success over more than 2 million years shows that evolution doesn't always move in a straight line toward increasing complexity. The diversity of Australopith species also reveals an important truth about human evolution. Our family tree is more of a family bush, with multiple lineages branching off, experimenting with different approaches to survival and sometimes coexisting in the same landscapes. This pattern of diversification would continue throughout human evolution, with multiple human species often living alongside each other. Perhaps most importantly, the Australopiths perfected bipedalism while maintaining their ability to climb trees when necessary. This versatility would prove crucial as Africa's climate continued to change. They developed the physical and behavioral foundations that would allow their descendants to eventually move beyond Africa and colonize new continents. But the world was changing around them. As the Pliocene epoch gave way to the Pleistocene around 2.6 million years ago, Africa was becoming cooler and drier. Grasslands were expanding, forests were shrinking, and new challenges were emerging. It was in this changing world that some Australopiths would make the leap to the next stage of human evolution. Chapter 3. Birth of the human genus. Imagine standing on the shores of Lake Turkana in Kenya 2.8 million years ago. The landscape stretches endlessly before you, a mosaic of grasslands, scattered trees, and sparkling water. In your hands you hold something that would seem insignificant to a casual observer, a simple piece of volcanic rock. But this rock has been deliberately shaped, its edges chipped away with purpose and precision to create a cutting edge. You are witnessing one of the most revolutionary moments in the history of life on Earth, the birth of technology. Evidence of tool-making dates to about 3.3 million years ago in Kenya. However, the age of the oldest remains of the genus Homo is younger than this technological milestone, dating to some 2.8 to 2.75 million years ago in Ethiopia. This seemingly simple innovation, the ability to deliberately modify natural objects to extend our capabilities, would ultimately allow a small African ape to dominate the planet. The makers of these first tools weren't quite like us yet. Their brains were still relatively small, their bodies still adapted for both walking and climbing. But in their hands, they held the future. They were the first members of our genus, Homo, and their story marks the beginning of a new chapter in the saga of human evolution, the emergence of the genus. Homo represents one of the most significant transitions in evolutionary history. The origin of the genus Homo in Africa signals the beginning of the shift from increasingly bipedal apes to primitive, large-brained, stone tool-making meat-eaters that traveled far and wide. This wasn't just an anatomical change. It was a fundamental shift in how our ancestors interacted with their environment. The earliest evidence of this transition comes from sites like Lonakvi 3 in Kenya, where archaeologists have discovered stone tools dating to 3.3 million years ago. These tools, known as the Lomquian industry, predate the earliest known Homo fossils by several 100,000 years, suggesting that toolmaking may have first developed among advanced Australopiths before being perfected by early Homo species. The tools themselves are remarkable for their simplicity and their sophistication. Made by striking one rock against another to create sharp flakes and cutting edges, they represent a level of cognitive complexity previously unknown in the animal kingdom. Creating these tools required not just manual dexterity, but also forward planning and understanding of cause and effect, and the ability to envision the final product before beginning the work. But who were the makers of these revolutionary implements? The earliest documented representative of the genus Homo is Homo habilis, which evolved around 2.8 million years ago, and is arguably the earliest species for which there is positive evidence of the use of stone tools. Homo habilis, whose name literally means handyman, represents the first species that we can definitively place within our own genus. The discovery of Homo habilis fundamentally changed our understanding of human evolution. Found primarily at sites in Tanzania and Kenya, these early humans showed a fascinating mixture of primitive and advanced characteristics. H. habilis is known for retaining primitive features that link it to Australopiths and for being the first stone tool makers. Their arms were still relatively long, their brains still relatively small, about 600 cubic centimeters, and their faces still quite projecting. Yet they had crossed a crucial threshold that would define all subsequent human evolution. The stone tools associated with Homo habilis belong to what archaeologists call the Oldowan industry, named after Olduvai Gorge in Tanzania, where many early examples were found. These tools might look crude to modern eyes, but they represent a quantum leap in cognitive evolution. Making an Oldowan tool requires understanding that a rock can be modified to serve a purpose, recognizing the best materials for the job, and possessing the fine motor control necessary to strike rocks together at precisely the right angle and force. But Homo habilis wasn't alone in early Africa. Around the same time, another species was emerging, Homo rudolfensis. The exact classification of Homo rudolfensis is debated, and some researchers consider it a distinct species, while others propose it may be a variation of Homo habilis. Known primarily from fossils found near Lake Turkana, formerly Lake Rudolph, this species had a larger brain and more robust features than H. habilis, leading some researchers to suggest it might represent a separate evolutionary experiment in early human evolution. The relationship between these early Homo species and their Australopith predecessors is still debated. It is generally agreed upon that H. habilis, spanning from 2.3 to 1.4 million years ago, is descended from a species of Australopithecus. If H. habilis evolved in East Africa, then Australopithecus afarensis and Australopithecus garhi are its possible ancestors. The diversity of potential ancestors suggests that the transition from Australopithecus to Homo may have happened multiple times, in different regions and in different ways. What drove this evolutionary transition? The answer likely lies in changing environmental conditions and dietary shifts. As Africa's climate became more variable during the Pleistocene, traditional food sources became less reliable. The ability to use tools would have provided a crucial advantage, allowing early humans to access new types of food, cracking open bones for marrow, cutting through tough plant materials, and processing foods that would otherwise be inedible. Evidence for this dietary shift can be seen in the anatomy of early Homo species. Their teeth show less emphasis on heavy chewing and more on slicing and cutting. Their skulls begin to show the gracile features that would characterize later human evolution. The partially preserved foot skeleton, O8, showed that H. habilis had fully adapted feet for walking bipedally, unlike preceding Australopiths, which still had some primitive traits, like a slightly divergent big toe, despite their regular, upright locomotion. But perhaps the most significant change was happening inside their skulls. The brains of these early hominins were about the same size as that of a chimpanzee, although it has been suggested that this was the time in which the human SRGAP2 gene doubled, producing a more rapid wiring of the frontal cortex. This genetic change may have laid the groundwork for the rapid brain expansion that would characterize later human evolution. The social implications of tool-making cannot be overstated. Tools aren't just individual innovations, they represent shared knowledge that must be transmitted from one generation to the next. This requires teaching, learning, and cultural transmission in ways that go far beyond what we see in other animals. Early Homo groups would have needed to develop new forms of communication and cooperation to effectively share technological knowledge. Archaeological evidence suggests that early Homo species were also beginning to expand their geographic range. Fossils and tools associated with early humans have been found across East Africa, from Ethiopia in the north to South Africa in the south. This expansion required not just physical adaptations, but also behavioral flexibility, the ability to adapt to new environments and exploit new resources. The tools themselves also began to evolve. While early old down tools were relatively simple, over time they became more sophisticated and standardized. This suggests that early humans were not just using tools, but actively improving them, a process that requires abstract thinking and the ability to envision better solutions to existing problems. One of the most remarkable aspects of early tool use is its association with evidence of meat consumption. Cut marks on bones found at early archaeological sites suggest that Homo habilis was using stone tools to process animal carcasses. Whether they were hunting these animals or scavenging from kills made by other predators is still debated, but the evidence clearly shows that meat was becoming an important part of their diet. This dietary shift may have been crucial for brain evolution. Brain tissue is metabolically expensive. It requires about 20% of our daily caloric intake, despite representing only 2% of our body weight. The high-quality protein and fats available from meat consumption may have provided the nutritional foundation necessary for the brain expansion that would characterize later human evolution. The emergence of Homo and the development of stone tool technology represents a fundamental turning point in the story of life on Earth. For the first time, a species was systematically modifying its environment, not through biological evolution, but through technological innovation. This marked the beginning of what we might call the co-evolution of humans and technology, a relationship that continues to shape our species today. The cognitive abilities required for tool-making, forward planning, abstract thinking, manual dexterity, and cultural transmission laid the foundation for all subsequent human achievements. Language, art, agriculture, and ultimately civilization all have their roots in the mental processes first developed by these early toolmakers. But toolmaking also had profound social implications. It required cooperation, teaching, and the development of increasingly sophisticated forms of communication. Early Homo groups would have needed to work together not just to make tools, but to share the knowledge of how to make them. This cooperative behavior would become one of the defining characteristics of human evolution. Chapter 4. First Steps Beyond Africa in 1891 on the banks of the Solo River in Java, Indonesia. A Dutch military doctor named Eugene Dubois made a discovery that would shake the scientific world to its core. Digging through ancient sediments, he uncovered a skull cap, a thigh bone, and several teeth that clearly belonged to something that was neither fully ape nor fully human. He called his discovery Pithecanthropus erectus, the upright ape man, though we know it today as Homo erectus. Early fossil discoveries from Java, beginning in the 1890s, and China, Peking man, beginning in the 1920s, comprise the classic examples of this species. What Dubois didn't realize at the time was that he had discovered evidence of humanity's first great adventure, the first time our ancestors had left their African homeland and set foot on distant continents. Homo erectus wasn't just another step in human evolution. They were pioneers, generally considered to have been the first species to have expanded beyond Africa. Homo erectus is considered a highly variable species, spread over 2 continents. It's not certain whether it reached Europe, and possibly the longest-lived early human species, about 9 times as long as our own species, Homo sapiens, has been around. For nearly 2 million years, they would call Asia home, adapting to environments their ancestors had never imagined. The story of Homo erectus begins in Africa around 1.9 million years ago, but it quickly becomes a tale of epic journeys and remarkable adaptations. These early humans were fundamentally different from their predecessors in ways that would prove crucial for their success as the first global human species. Early African Homo erectus fossils, sometimes called Homo ergaster, are the oldest known. Early humans to have possessed modern human-like body proportions with relatively elongated legs and shorter arms compared to the size of the torso. These features are considered adaptations to a life lived on the ground, indicating the loss of earlier tree-climbing adaptations, with the ability to walk and possibly run long distances. The most complete fossil individual of this species is known as the Turkana boy, a well-preserved skeleton dated around 1.6 million years old. This remarkable discovery provides an unprecedented window into the anatomy and lifestyle of early Homo erectus. Standing nearly 6 feet tall, Turkana boy was probably only about 9 years old when he died, suggesting that adult H. erectus would have been impressively tall by the standards of earlier human species. The anatomy of Homo erectus tells a story of remarkable adaptation. H. erectus crania are distinct from H. habilis first and foremost by their larger brain size, 700 to 1,300 cubic centimeters, which begins small and increases through time. This represents a significant leap forward, nearly double the brain size of their predecessors. But it wasn't just brain size that changed. The entire structure of their skulls reflected their advancing intelligence. They have a thicker brow ridge, which sometimes forms a bony shelf called a supraorbital torus, and the frontal bone, above the brow ridge, recedes toward the back. The overall shape of the H. erectus cranium is long and low, like an American football, compared to a round H. sapiens cranium, which is relatively more like a soccer ball. These features give H. erectus skulls a distinctive appearance that bridges the gap between earlier human species and modern humans. But perhaps the most revolutionary aspect of Homo erectus was their relationship with technology. Soon after, we see evidence in the fossil record of the earliest Homo erectus fossils by about 1.9 million years ago. We see evidence in the archaeological record for the first major innovation in stone tool technology by about 1.76 million years ago. Known as the Acheulean stone tool industry, it consisted of the creation of large cutting tools like hand axes and cleavers. These Acheulean tools represent a quantum leap in technological sophistication. Unlike the simple choppers and scrapers of the old Daoan tradition, Acheulean hand axes required advanced planning, three-dimensional thinking, and remarkable skill to create. A typical hand axe was carefully shaped on both sides to create a symmetrical, teardrop-shaped tool with sharp edges along its entire perimeter. Making such a tool required the ability to envision the final product before beginning work and the patience to remove dozens of flakes in a precise sequence. The consistency of Acheulean tools across vast distances and time spans is remarkable. Nearly identical hand axes have been found from Africa to India to England, spanning more than 1 million years of human history. This standardization suggests not just individual skill, but cultural transmission, the ability to teach and learn. Complex technological procedures across generations and geographic distances. Perhaps even more significant was Homo erectus' mastery of fire. The earliest evidence of hearths, campfires, occurred during the time range of Homo erectus. While we have evidence that hearths were used for cooking and probably sharing food, they are likely to have been places for social interaction and also used for warmth and to keep away large predators. The control of fire was arguably one of the most important technological advances in human history, comparable to the invention of agriculture or the wheel. Fire provided Homo erectus with capabilities that no other animal possessed. It allowed them to extend their day into the night, cook food to make it more digestible and nutritious, and most importantly for their global expansion, survive in climates that would otherwise have been too cold for tropical animals. Fire was the technology that made their migration out of Africa possible. The Great Migration began around 1.8 million years ago, making Homo erectus the first human species to expand beyond Africa. The earliest evidence for this expansion comes from the site of the Menisi in Georgia, where remarkably complete skulls and skeletons have been found dating to about 1.8 million years ago. Cast of Skull 5, D4500, the most complete Homo erectus. Skull found at the Menisi, Georgia, on display in the museum's Human Evolution Gallery. The original fossil skull is about 1.8 million years old. The Menisi fossils are particularly important because they capture Homo erectus at the very beginning of their expansion out of Africa. These early immigrants were still quite primitive. In many respects, their brains were smaller than later H. erectus populations, and their tools were still relatively simple. Yet they had already developed the biological and cultural adaptations necessary to survive in entirely new environments. From the Caucasus, Homo erectus continued their expansion eastward across Asia. The species spread into Eastern Asia, including China, where it appears to have been present until at least 300,000 years ago. The famous Peking Man fossils from Zhaokutian Cave near Beijing provide evidence of sophisticated H. erectus populations living in China between 750,000 and 300,000 years ago. These populations had developed advanced hunting techniques, sophisticated use of fire, and possibly even early forms of symbolic behavior. In Southeast Asia, H. erectus was a long-term inhabitant of Java. H. erectus fossils there date from about 1.6 million years to at least 250,000 years ago. The species may have survived more recently in Taiwan, the Philippines, and on the Indonesian island of Sulawesi, but the evidence isn't conclusive. Some evidence suggests that isolated populations of H. erectus may have survived until as recently as 100,000 years ago, making them contemporaries of early modern humans. The success of Homo erectus as a global species is truly remarkable. In terms of species survival, Homo erectus is a huge success story. Fossil evidence for H. erectus stretches over more than 1.5 million years, making it by far the longest surviving of all our human relatives. Compare this to our own species, Homo sapiens, which has been around for perhaps 400,000 years so far, and we begin to appreciate their ability to survive over a long period, marked by many changes to the environment and climate. This longevity and geographic spread came at a cost, however. As Homo erectus populations spread across different continents and adapted to different environments, they began to diverge from each other. The fossils from Java look somewhat different from those found in China, which in turn differ from African specimens. This geographic variation was likely the beginning of the evolutionary processes that would eventually lead to the emergence of multiple human species. Evidence also suggests that Homo erectus developed increasingly sophisticated behaviors over time. There is fossil evidence that this species cared for old and weak individuals, suggesting a level of social cooperation and empathy that goes beyond simple survival. Archaeological sites show evidence of organized living spaces, with different areas designated for different activities: tool-making, food preparation, and sleeping areas. Some researchers have even suggested that late Homo erectus populations may have developed early forms of symbolic behavior, though this remains controversial. Marks found on shells from Java have been interpreted by some as intentional geometric patterns, though others argue they could be the result of natural processes or accidental damage. Chapter 5: Neanderthals and the Frozen World. Picture Europe 400,000 years ago. Vast ice sheets stretching south from the Arctic, mammoths trudging across endless tundra, and cave bears the size of small cars prowling through forests of pine and birch. This was a world that would kill most tropical species within days, a landscape of survival challenges that make modern wilderness adventures look like leisurely strolls. Yet in the caves and rock shelters scattered across this frozen continent, a fire crackles against the darkness. Around it huddle figures that look almost, but not quite, like modern humans. Their brows are heavy, their faces project forward, and their bodies are compact and powerfully built. They are crafting spear points with a precision that would impress modern artisans, planning hunting strategies that require complex understanding of animal behavior, and caring for elderly and disabled members of their communities with a compassion that speaks to deep emotional complexity. These are the Neanderthals, Homo neanderthalensis, and their story represents one of the most remarkable survival sagas in human history. Neanderthals, Homo neanderthalensis, were archaic humans who emerged at least 200,000 years ago and died out perhaps between 35,000 and 24,000 years ago. For over 400,000 years, they would rule the challenging landscapes of Ice Age Europe and parts of Asia, developing a sophisticated culture perfectly adapted to one of the harshest environments our planet has ever known. The Neanderthal story begins around 800,000 years ago when Homo erectus populations in Europe began to evolve in isolation from their African relatives. Around 600 KE, Europe was invaded by large-brained hominins using Acheulean stone tools. 1-2. They were probably African immigrants because similar fossils and tools occur earlier in Africa. These early Europeans faced unprecedented challenges as the planet entered a period of regular ice ages, and their evolutionary response would create one of the most specialized human species ever to exist. The oldest recovered DNA of an early human relative comes from Cima de los Huesos, pit of bones. At the bottom of a cave in Spain's Atapuerca Mountains, scientists found thousands of teeth and bones from 28 different individuals who somehow ended up collected en masse. In 2016, scientists painstakingly teased out the partial genome from these 430,000-year-old remains to reveal that the humans in the pit are the oldest known Neanderthals. Our very successful and most familiar close relatives date by 430,000 years ago. The earliest clearly identifiable Neanderthals had emerged. These early Neanderthals already showed many of the distinctive features that would characterize the species: robust builds, large brain cases, and faces adapted for life in cold climates. Their evolution from earlier European populations represents one of the clearest examples of human adaptation to extreme environmental conditions. Neanderthal anatomy tells a story of remarkable specialization for cold climates. Their bodies were compact and muscular, with short limbs relative to their torsos, an adaptation that minimized heat loss in frigid conditions. Their large noses weren't just prominent features. They were sophisticated heating and humidifying systems that warmed and moistened the bitter Arctic air before it reached their lungs. Perhaps most remarkably, Neanderthal brains were actually larger than those of modern humans. Neanderthals with 1,200 to 1,900 cc, 73 to 116 cu in, larger even than modern Homo sapiens. This brain increase manifested during postnatal brain growth, far exceeding that of other apes, heterochrony. Their skulls had to accommodate these massive brains, resulting in the distinctive elongated shape that characterizes Neanderthal fossils. But what were they doing with all that brain power? The archaeological record reveals a species of remarkable sophistication. They manufactured and used tools, including blades, awls, and sharpening instruments, developed a spoken language, and developed a rich culture that involved hearth construction, traditional medicine, and the burial of their dead. Their stone tool technology, known as the Mousterian industry, was far more sophisticated than anything produced by earlier human species. Neanderthal tools were made using a technique called the Lavalval method, which required advanced planning and three-dimensional thinking. Toolmakers would carefully prepare a stone core, then strike it at precisely the right angle to produce flakes of predetermined size and shape. This technique allowed them to produce tools that were consistently sharp and could be easily resharpened when they became dull. Evidence suggests that Neanderthals were also skilled hunters capable of taking down some of the most dangerous prey animals of the Ice Age. Sites throughout Europe contain evidence of successful hunts of mammoths, woolly rhinoceros, cave bears, and other massive herbivores. These hunts required not just physical courage, but sophisticated planning, coordination, and understanding of animal behavior. One of the most compelling aspects of Neanderthal culture is their care for community members. Fossil evidence shows that Neanderthals cared for disabled and elderly individuals who would have been unable to contribute to group survival. The famous Shanidar, one skeleton from Iraq, shows evidence of multiple injuries and disabilities that would have required long-term care from the community. This level of compassion and social cooperation suggests emotional and cognitive complexity that rivals that of modern humans. Even more intriguingly, Neanderthals also created art. Evidence shows that some painted with naturally occurring pigments. Cave paintings in Spain have been dated to 65,000 years ago, long before modern humans arrived in Europe. These paintings include hand stencils, geometric patterns, and representations of animals, suggesting that Neanderthals possessed symbolic thinking and possibly spiritual beliefs. The evidence for Neanderthal burial practices is particularly compelling. At sites across Europe and the Middle East, Neanderthal remains have been found in deliberate grave contexts, sometimes with apparent grave goods or evidence of ritual behavior. The famous Shanidar 4 burial in Iraq was found surrounded by flower pollen, leading some researchers to suggest that Neanderthals buried their dead with flowers, though this interpretation remains controversial. Perhaps most remarkably, recent genetic research has revealed that Neanderthals possess the FOXP2 gene variant associated with advanced language abilities in modern humans. This, combined with their large brains and sophisticated tool-making abilities, suggests that they may have possessed complex spoken language. The structure of their hyoid bones, which support the voice box, also suggests that they were capable of producing the full range of sounds necessary for articulate speech. But Neanderthals weren't just successful survivors. They were innovators. Evidence from various sites suggests they developed specialized technologies for different environments and resources. Coastal populations appear to have harvested shellfish and marine resources, while inland groups developed specialized hunting techniques for different types of prey. Some Neanderthal populations even showed evidence of long-distance trade or cultural exchange. Ornamental shells and pigments have been found hundreds of kilometers from their sources, suggesting either trade networks or long-distance travel. This level of cultural complexity challenges earlier assumptions about Neanderthal cognitive abilities. Recent discoveries have also revealed the full extent of Neanderthal geographic range. Once thought to be confined to Europe, Neanderthal fossils and tools have now been found from the Atlantic coast of Portugal to the Altai Mountains of Siberia. Some populations even reached the Middle East, where they would eventually encounter migrating populations of modern humans. The interaction between Neanderthals and modern humans represents one of the most fascinating chapters in human evolution. For decades, scientists debated whether these two species ever met, let alone interbred. That question was definitively answered in 2010 with the sequencing of the Neanderthal genome, which revealed that modern humans and Neanderthals didn't just cross paths. They repeatedly interbred, shared genes, and even merged populations over nearly 250,000 years. The evidence of this genetic resistance shows that there have been at least 3 incursions of non-human DNA into the genes for immune response. 2 coming from Neanderthals and 1 from our poorly understood evolutionary cousins, the Denisovans. Modern humans today carry between 1 to 4% Neanderthal DNA, with the highest percentages found in East Asian populations. This genetic legacy isn't just a historical curiosity, it has real impacts on modern human health and biology. Some Neanderthal genes appear to have provided advantages to modern human populations, particularly in areas related to immune function and adaptation to non-African environments. However, other Neanderthal alleles have become problematic in modern contexts, contributing to increased risks of depression, blood clots, and other health issues. Recent research using a high-powered genetic analysis has revealed an even more complex picture of Neanderthal-modern human interaction. Led by Joshua Aki, a professor at Princeton's Louis Sigler Institute for Integrative Genomics, the team has found strong evidence of genetic exchange between early human groups, pointing to a much deeper and more complex relationship than previously understood. They discovered that a Neanderthal from Vindija, Croatia, had about 2.5% modern human DNA in its genome, and another Neanderthal from the Altai Mountains in Siberia had about 3.7% modern human DNA. Chapter 6: Denisovans and the Roof of the World. High in the Altai Mountains of Siberia, at an elevation where the air is thin and winter temperatures plunge to -40°F, lies a cave that has preserved one of the most remarkable stories in human evolution. Denisova Cave doesn't look like much from the outside, just another rocky opening in the mountainside. But within its cool, dark chambers lies evidence of a human population so mysterious that until 2010, We didn't even know they existed then. That year, a team of scientists led by Svante Pääbo extracted DNA from what appeared to be an unremarkable finger bone fragment. What they discovered would revolutionize our understanding of human evolution. The genome belonged to neither a modern human nor a Neanderthal, but to an entirely unknown human lineage. They called them DENISOVANS after the cave where they were found. Since that groundbreaking discovery, evidence for Denisovans has emerged from some of the most extreme environments on Earth, from the 15,000-foot-high Tibetan Plateau to the tropical forests of Southeast Asia. These ancient humans weren't just survivors. They were master adapters who conquered ecological niches that would challenge even modern humans equipped with advanced technology. Their story reveals the incredible flexibility of human evolution and the remarkable diversity of our ancient relatives. The Denisovan story begins with a mystery wrapped in an enigma. Unlike Neanderthals, who left behind thousands of fossils across Europe and Asia, Denisovans are known primarily from a handful of bone fragments and teeth from a single cave in Siberia. Yet their genetic legacy tells a story of remarkable success and geographic spread that rivals that of any human species. Sequenced mitochondrial DNA, mtDNA, preserved by the cool climate of the cave, average temperature is at freezing point, was extracted from Denisova 3 by a team of scientists led by Johannes Krause and Svante Pääbo from the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany. The results were startling. This DNA was clearly human, but it differed from both modern humans and Neanderthals by margins that suggested a separate evolutionary lineage stretching back hundreds of thousands of years. The relationship between Denisovans and other human species is complex and still being unraveled. H. heidelbergensis is typically considered to have been the direct ancestor of Denisovans and Neanderthals, and sometimes also modern humans. Due to the strong divergence in dental anatomy, they may have split before characteristic Neanderthal dentition evolved about 300,000 years ago. Using genetic molecular clocks, scientists estimate that Denisovans and Neanderthals separated around 400,000 to 600,000 years ago, both lineages having earlier separated from the ancestors of modern humans. But the scarcity of Koresvidov Denisovan fossils makes understanding their physical appearance and lifestyle extremely challenging. There are not enough Denisovan fossils and genomes to have as clear a picture of their species as we do Neanderthals. The few physical remains we have suggest they were robust, cold-adapted humans with large teeth and strong jaws. But beyond these basic features, much about their anatomy remains mysterious. What we do know comes primarily from their remarkable genetic legacy. Denisovan-derived ancestry is largely absent from modern populations in Africa, Western Asia, and Europe. The highest rates by far of Denisovan admixture have been found in Oceanian and some Southeast Asian populations. An estimated 4 to 6% of the genome of modern Melanesians is derived from Denisovans, but the highest amounts detected thus far are found in the Negrito populations of the Philippines. This genetic distribution tells a story of incredible geographic spread and adaptation. Denisovans weren't confined to the cold mountains of Siberia. They ranged across much of Asia, from the Arctic to the tropics. This geographic diversity suggests remarkable adaptability and possibly multiple distinct Denisovan populations adapted to different environments. Perhaps the most compelling evidence for Denisovan adaptability comes from their genetic contributions to modern high-altitude populations. A gene variant inherited from Denisovans, present today in Tibetan populations, may enable better survival at high altitudes. The EPase1 gene variant, found in up to 87% of modern Tibetans, helps regulate red blood cell production at high altitudes where oxygen is scarce. This adaptation allows Tibetans to thrive at altitudes above 14,000 feet, where most people would suffer from severe altitude sickness. The presence of this high-altitude adaptation in Denisovan DNA, combined with recent archaeological discoveries, suggests that Denisovans were the first humans to successfully colonize the high-altitude environments of the Tibetan Plateau. Archaeological evidence from the Shaya cave on the Tibetan Plateau has yielded a Denisovan mandible, lower jaw, dating to at least 160,000 years ago, direct proof that Denisovans were living at extreme altitudes long before modern humans arrived. In the region, recent discoveries have revealed even more about Denisovan diversity and longevity. In 2022, a team from Germany, Austria, Russia, and the UK found 3 Denisovans, Denisovan 19-20-21, from layer 15 of the East Chamber in Denisova Cave. It turns out that the mtDNA sequences of Denisova 19 and 21 are identical, indicating that they may belong to the same individual or be maternal relatives. The genetic diversity among the Denisovans from Denisova Cave is on the lower range of what is seen in modern humans, and is comparable to that of Neanderthals. However, it is possible that the inhabitants of Denisova Cave were more or less reproductively isolated from other Denisovans, and that, across their entire range, Denisovan genetic diversity may have been much higher. Evidence suggests that Denisovans weren't just high-altitude specialists, they were technological innovators as well. In 2025, archaeologists discovered an assemblage of 35 wooden implements on the shores of an ancient lake from the site of Gantanging in Yunnan, southwestern China, which was found associated with stone tools, antler billets, soft hammers, and cut-marked bones, and is dated from approximately 361,000 to 250,000 years at a 95% confidence interval, at a time when Denisovans were known to have inhabited the general region. The wooden implements include digging sticks made of pine and hardwood, hooks for cutting roots, and small, complete, handheld pointed tools. Our results suggest that hominins at Gantanging made strategic utilization of lakeshore food resources, the researchers wrote in the study. This evidence suggests sophisticated resource management and possibly seasonal rounds of resource exploitation, behaviors that require advanced planning and environmental knowledge. The interaction between Denisovans and other human species appears to have been even more complex than that between Neanderthals and modern humans. These ancient encounters weren't one-off events either. Scientists have now found traces of at least 3 separate Denisovan human interbreeding episodes. The genetic evidence suggests multiple distinct Denisovan populations that interbred with different groups of modern humans at different times and places. One of the most remarkable discoveries was made in 2018. The first known, first-generation hybrid between 2 different ancient human species. A female who died around 90,000 years ago was half Neanderthal and half Denisovan, according to genome analysis of a bone discovered in a Siberian cave. This is the first time scientists have identified an ancient individual whose parents belonged to distinct human groups. This discovery proves that these ancient human species weren't just coexisting, they were actively interbreeding and forming mixed communities. The genetic contributions of Denisovans to modern humans extend far beyond high-altitude adaptation. Remarkably, Denisovan genes helped us adapt to life in extreme environments, from high-altitude Tibet to the icy Arctic, granting us better oxygen use, stronger immune systems, and cold resistance. In Papuans, Neanderthal genetic variants are found in highest frequency in genes expressed in the brain, whereas Denisovan DNA has the highest frequency in genes expressed in bones and other tissues. Some research suggests that Denisovan genetic contributions may have been crucial for the successful colonization of previously uninhabitable environments. The Arctic adaptations found in modern Inuit populations may have been inherited from Denisovan populations that had already adapted to extreme cold. Similarly, immune system variants that help modern Southeast Asian populations resist tropical diseases may have Denisovan origins. The story of Denisovan technological and cultural capabilities is still being written. Recent genetic analysis has revealed that Denisovans, like Neanderthals, possess genetic variants associated with advanced cognitive abilities. The AMY1 gene produces salivary amylase, an enzyme that helps us digest starches in food like grains and potatoes. Faiza Yilmaz and colleagues found that the AMY1 gene multiple copy number adaptation actually emerged around 800,000 years ago, 500,000 years before Homo sapiens even existed. They found increased copy numbers of the AMY1 gene in 3 Neanderthal genomes, 2.6 to 5 copies, and 1 Denisovan, GENOM, E8 copies. This suggests that Denisovans had developed sophisticated food processing techniques and possibly even early forms of plant cultivation. The ability to efficiently digest starchy plants would have been crucial for survival in the diverse environments they inhabited, from the protein-poor high-altitude regions to the carbohydrate-rich tropical forests. The Denisovan story represents one of the most remarkable examples of human adaptability and diversification. Despite being known from only a handful of fossil fragments, their genetic legacy reveals a human lineage that successfully colonized some of the most challenging environments on Earth, from the oxygen-thin air of the Tibetan Plateau to the dense tropical forests of Southeast Asia. Denisovans developed biological and cultural adaptations that allowed them to thrive where other species struggled to survive. Perhaps most significantly, the Denisovan legacy demonstrates that human evolution was far more complex and interconnected than previously imagined. Rather than a simple linear progression from early humans to modern humans, the story reveals a rich tapestry of interbreeding, cultural exchange, and genetic mixing between multiple human lineages. The genetic contributions of Denisovans to modern human populations highlight the importance of hybridization in human evolution. Many of the adaptations that allow modern humans to live in extreme environments, from the high Andes to the Arctic tundra, may have been inherited from ancient human populations that had spent hundreds of thousands of years developing these specialized traits. As we continue to discover new evidence of Denisovan presence across Asia and analyze their genetic contributions to modern populations, their story serves as a reminder of the incredible diversity and adaptability that has characterized human evolution throughout our history. As Denisovans mastered the heights of Asia and Neanderthals ruled the frozen landscapes of Europe, the stage is being set for the emergence of the most successful human species of all, Homo sapiens. Around 300,000 years ago, in the changing landscapes of Africa, a new type of human was evolving, one that would combine the adaptability of earlier species with revolutionary new capabilities in language, abstract thinking, and cultural innovation. This new species would not only survive the challenges that drove their ancient relatives to extinction, but would ultimately spread across the entire globe, becoming the only human species to survive to the present day. Chapter 7. Rise of modern humans in the windswept hills of Morocco. 300,000 years ago, a group of humans gathered around a fire outside a cave mouth. At first glance, they might not look dramatically different from their Neanderthal cousins. Living far to the north, they were robust, tool-making hunters with brains nearly as large as our own. But if you looked closely, you would notice something revolutionary in their behavior. These humans were creating something unprecedented: symbolic artifacts. They were making pigments from red ochre, carving marks into pieces of bone, and possibly even creating the first jewelry from perforated shells. Most remarkably, They were developing something that would change the course of life on Earth forever: complex grammatical language. The oldest known remains of Homo sapiens, a collection of skull fragments, a complete jawbone, and stone tools, date to about 315,000 years ago. These are our direct ancestors, the first members of Homo sapiens, and their emergence marks the beginning of the final chapter in human evolution. Modern humans evolved in Africa around 200,000 years ago. They have a higher and more rounded brain case, smaller faces and brow ridges, and a more prominent chin than other ancient humans. But what made Homo sapiens different wasn't just anatomy. It was a revolution in thinking, communication, and culture that would ultimately make us the dominant species on the planet. The emergence of Homo sapiens represents the culmination of millions of years of human evolution, but also the beginning of something entirely new in the history of life on Earth. Modern human ancestors diverged from the ancestors of Neanderthals and Denisovans about 600,000 years ago. Until about 40,000 years ago, these three groups existed in parallel, occasionally met and exchanged genes. A critical question is why modern humans, and not the other two groups, survived, became numerous, and developed complex cultures. The earliest evidence for anatomically modern humans comes from sites across Africa, with the oldest remains found at Jebel Irhoud in Morocco, dating to approximately 315,000 years ago. These early Homo sapiens already possessed the distinctive features that define our species: a high, rounded forehead, a vertical face with reduced brow ridges, a prominent chin, and a gracile overall build. But what truly set Homo sapiens apart wasn't visible in their skeletons, it was their behavior. The archaeological record from early modern human sites reveals innovations that had never before appeared in human evolution. These include the systematic production of pigments, the creation of personal ornaments, sophisticated blade tool technologies, and evidence of long-distance trade networks. One of the most significant developments was the emergence of complex symbolic behavior. Evidence from sites like Blombos Cave in South Africa, dating to around 75,000 years ago, reveals abstract geometric patterns carved into pieces of ochre, some of the earliest known examples of symbolic art. These patterns aren't random scratches. They show clear evidence of planning, repetition, and possibly meaning. This represents a cognitive revolution that would ultimately separate modern humans from all other species. The development of language may have been the most crucial innovation of all. While earlier human species certainly communicated and may have had simple proto-languages, modern humans developed something unprecedented: fully grammatical language with unlimited expressive potential. Modern humans have a complex vocal apparatus that allows for advanced language and communication. This wasn't just an improvement in communication. It was a fundamental transformation that allowed for the storage and transmission of vastly more complex cultural information. Language enabled what anthropologists call cumulative culture, the ability to build on previous innovations and pass increasingly sophisticated knowledge from generation to generation. Unlike other species, where each generation must largely relearn survival skills through trial and error, modern humans could transmit detailed technical knowledge, complex strategies, and abstract concepts through spoken language. This cultural revolution coincided with remarkable technological innovations. Early modern humans developed blade tool technologies that were far more sophisticated and efficient than anything produced by earlier species. These tools required advanced planning and were often made using carefully prepared raw materials transported over long distances. Some blade tools were so standardized that they appeared to represent specific brands or cultural traditions that persisted for thousands of years. Perhaps even more remarkably, early modern humans began creating personal ornaments and art objects. The use of ornaments beads 110K. Image is of 8 beads made out of shells with a small hole in each bead. These weren't just decorative. They were markers of individual and group identity, evidence of self-awareness and social complexity that had never before existed in human evolution. The emergence of modern humans in Africa wasn't a single event, but rather a complex process that may have involved multiple populations across the continent. To understand how Homo sapiens eventually evolved from these older lineages of hominins, the group including modern humans and our closest extinct relatives and ancestors, scientists are unearthing ancient bones and stone tools, digging into our genes and recreating the changing environments that helped shape our ancestors' world and guide their evolution. These lines of evidence increasingly indicate that H. sapiens originated in Africa, although not necessarily in a single time and place. Instead, it seems diverse groups of human ancestors lived in habitable regions around Africa, evolving physically and culturally in relative isolation, until climate-driven changes to African landscapes spurred them to intermittently mix and swap. Everything from genes to tool techniques. Eventually, this process gave rise to the unique genetic makeup of modern humans. This African multi-regional model suggests that early modern humans evolved through the interaction of multiple populations across Africa rather than in a single location. Genetic evidence supports this view, showing that modern African populations retain more genetic diversity than any other human populations. Evidence of a deep and complex evolutionary history within the continent. The archaeological record reveals that early modern humans were developing increasingly sophisticated hunting and gathering strategies. They were among the first humans to systematically exploit marine resources, collecting shellfish and developing technologies for deep-sea fishing. They invented new hunting technologies, including spear throwers that dramatically increased the range and accuracy of projectile weapons. Evidence also suggests that early modern humans developed more complex social structures than their predecessors. Symbolic behavior mortuary modification of human skeletal remains 160. Ka suggests that they were developing beliefs about death and possibly an afterlife. Some burial sites contain evidence of grave goods, tools, ornaments, and pigments placed, with the deceased indicating complex social hierarchies and spiritual beliefs. Perhaps most remarkably, early modern humans began creating what we can only call art. Cave paintings, carved figurines, and musical instruments appear in the archaeological record, beginning around 40,000 years ago, but their roots likely extend much deeper. These artistic expressions weren't just decorative. They represent abstract thinking, symbolic communication, and possibly spiritual or religious beliefs. The success of early modern humans wasn't just cultural, it was also biological. Genetic studies reveal that modern humans possess several key advantages over their contemporaries. They appear to have had more efficient metabolisms, allowing them to extract more energy from food. Their immune systems were more adaptable, helping them survive exposure to new diseases as they expanded into new environments. Most importantly, modern humans seem to have had greater genetic diversity than other contemporary human species. This diversity provided a larger pool of genetic variants that could be selected for as humans encountered new environmental challenges. While Neanderthal and Denisovan populations appear to have suffered from the genetic effects of small population sizes in isolation, early modern humans maintained larger, more interconnected populations that were more genetically robust. The expansion of modern humans out of Africa began around 70,000 to 100,000 years ago, though there may have been earlier, unsuccessful attempts. Unlike earlier human migrations, this expansion was characterized by rapid adaptation to new environments and the development of specialized technologies for different regions. The first successful migrations appear to have followed coastal routes, around the Red Sea and along the coasts of Arabia and India. These early migrants were sophisticated seafarers who developed technologies for ocean travel and coastal resource exploitation. Archaeological evidence suggests they reached Australia by at least 50,000 years ago, a journey that required sophisticated boat-building technology and navigational skills. As modern humans spread across the globe, they encountered and interbred with local populations of archaic humans. We know that interbreeding with these ancient humans allowed Homo sapiens to acquire genes that improved their chances of survival, and some of these genes remain in many of us today. The introgression events into modern humans are estimated to have happened about 47,000 to 65,000 years ago with Neanderthals and about 44,000 to 54,000 years ago with Denisovans. This genetic mixing wasn't just incidental, it appears to have been crucial for the success of modern humans in new environments. Genes inherited from Neanderthals provided advantages for survival in cold climates and resistance to certain diseases. Denisovan genes provided adaptations for high-altitude living and possibly other environmental challenges. But the success of modern humans came at a cost. As they spread across the globe, other human species began to disappear. Despite the bits of genetic ancestry they contributed to living people, all of our close relatives eventually died out, leaving Homo sapiens as the only human species. Their extinctions add one more intriguing, perhaps unanswerable question to the story of our evolution. Why were we the only humans to survive? The emergence and global spread of modern humans represents the culmination of human evolution and the beginning of recorded history. The cognitive and cultural revolutions that characterized early Homo sapiens provided the foundation for all subsequent human achievements, from agriculture and civilization to art and science. Perhaps most importantly, the success of modern humans demonstrates the power of culture as an evolutionary force. While earlier human species adapted to new environments, primarily through biological evolution, developing new physical traits over many generations, modern humans adapted primarily through cultural innovation. This allowed them to colonize new environments in a matter of decades rather than millennia. The genetic legacy of interbreeding with archaic humans also highlights the importance of hybridization in recent human evolution. Rather than simply replacing earlier human species, modern humans absorbed many of their advantageous traits through interbreeding. This genetic mixing may have been crucial for the rapid adaptation of modern humans to diverse global environments. The story of modern human emergence also reveals the importance of Africa in human evolution. Not only did our species originate in Africa, but the continent continues to harbor the greatest genetic diversity of any human population. Understanding African genetic diversity remains crucial for understanding human evolution and adaptation. As modern humans spread across the globe between 70,000 and 50,000 years ago, they were entering a world already populated by their ancient relatives. The story of what happened next, the encounters, conflicts, and ultimately the absorption of these archaic human populations represents one of the most dramatic and consequential chapters in human history. These ancient meetings would reshape both the genetics and culture of our species, leaving legacies that continue to influence human biology and behavior today. The age of multiple human species was coming to an end, but not before these final interactions would fundamentally alter the course of human evolution. Chapter 8. When human worlds collided. Imagine standing at the entrance to a cave in southern France, 45,000 years ago. The landscape before you is a patchwork of grasslands and forests, where mammoth herds thunder across the plains and cave bears prowl through ancient woods. But something extraordinary is happening in this Ice Age world. For the first time in hundreds of thousands of years, multiple human species are sharing the same landscape. In the caves and rock shelters scattered across Europe, Neanderthals continue their ancient way of life, as they have for over 400,000 years. They are master survivors, perfectly adapted to this frozen world. But now, emerging from the forest with technologies and behaviors never before seen, come the newcomers, modern humans, fresh from their African homeland, carrying with them innovations that will change everything. This is the story of the Great Convergence, the period between roughly 50,000 and 30,000 years ago, when modern humans encountered and ultimately absorbed the last surviving populations of archaic humans. It wasn't a simple conquest or replacement. It was a complex process of interaction, interbreeding, and cultural exchange that would fundamentally reshape human evolution and leave its mark, our DNA, forever. For thousands of years, these different human species would share the same landscapes, and their encounters would determine which lineages would survive into the modern era. The Great Convergence began around 50,000 years ago as modern humans, equipped with revolutionary new technologies and cultural innovations, began expanding out of Africa and into territories that have been occupied by archaic human populations for hundreds of thousands of years. This wasn't humanity's first attempt to leave Africa. Earlier migrations had occurred around 100,000 years ago, but this time would be different. This time, modern humans possessed the cultural and technological tools necessary for permanent success. The evidence for these ancient encounters told me from multiple sources: archaeological sites that show sudden changes in tool technologies, genetic studies that reveal the timing and extent of interbreeding, and fossil sites that capture moments of cultural exchange between different human populations. Recent research using AI-powered genetic analysis has revealed an even more complex picture of these interactions than previously imagined. Led by Joshua Aki, a professor at Princeton's Louis Sigler Institute for Integrative Genomics. Recent studies have found strong evidence of genetic exchange between early human groups, pointing to a much deeper and more complex relationship than previously understood. Modern humans have been interbreeding with Neanderthals for more than 200,000 years, with multiple waves of contact occurring over 250,000 years. Aki and Lee identified a first wave of contact about 200 to 250,000 years ago, another wave 100 to 120,000 years ago, and the largest one about 50 to 60,000 years ago. The most dramatic encounters occurred in Europe, where modern humans encountered Neanderthal populations that had been evolving in isolation for nearly 400,000 years. Archaeological evidence suggests that these encounters weren't always peaceful. At some sites, we see evidence of rapid technological change as Neanderthal populations began adopting tools and techniques previously associated only with modern humans. This suggests direct cultural exchange and possibly cooperation between the two species. At other sites, however, the evidence suggests more competitive interactions. The archaeological record shows that Neanderthal populations began declining shortly after modern humans arrived in their territories. Some researchers have suggested that modern humans may have had competitive advantages that allowed them to outcompete Neanderthals for resources, leading to gradual population replacement. But the genetic evidence tells a more complex story. Rather than simple replacement, what occurred was extensive interbreeding and genetic mixing. The vast majority of genetic work over the last decade has really focused on how mating with Neanderthals impacted modern human phenotypes and our evolutionary history. But recent research has looked at the reverse: how modern human genes affected Neanderthal populations. This research has revealed that gene flow occurred in both directions. They discovered that a Neanderthal from Vindisia, Croatia, had about 2.5% modern human DNA in its genome, and another Neanderthal from the Altai Mountains in Siberia had about 3.7% modern human DNA. This shows that Neanderthals weren't just passive. recipients of modern human genes. They were active participants in a complex process of genetic and cultural exchange. The encounters with Denisovans were even more geographically dispersed and complex. As modern humans spread across Asia, they encountered Denisovan populations adapted to environments ranging from the cold mountains of Siberia to the tropical highlands of Southeast Asia. These ancient encounters weren't one-off events either. Scientists have now found traces of at least 3 separate Denisovan human interbreeding episodes. Perhaps the most remarkable discovery was made in Denisova Cave itself, the first known individual who was the direct offspring of parents from 2 different ancient human species. A female who died around 90,000 years ago was half Neanderthal and half Denisovan, according to genome analysis of a bone discovered in a Siberian cave. This discovery proves that these ancient human encounters weren't just occasional meetings. They involved the formation of mixed communities where individuals from different species lived, worked, and raised families together. The cultural implications of these encounters were profound. Archaeological evidence suggests that contact with modern humans triggered innovations among archaic human populations. Some late Neanderthal sites show evidence of new tool technologies, symbolic behaviors, and even art forms that appear to have been adopted from modern human populations. At the same time, modern humans appear to have learned from their archaic relatives. Tools and techniques that first appeared in Neanderthal contexts later show up in modern human archaeological sites, suggesting cultural transmission in both directions. Some researchers have even suggested that certain modern human hunting techniques and cold weather adaptations may have been learned from Neanderthal populations. The genetic contributions from these encounters had immediate and long-lasting impacts on modern human populations. Some of the DNA inherited from Neanderthals seems to have been involved in boosting immunity. For example, while a gene variant inherited from Denisovans present today in Tibetan populations may enable better survival at high altitudes, these genetic contributions weren't random. Natural selection appears to have favored certain archaic human genes while eliminating others. Genes related to immune function were particularly likely to be retained, suggesting that archaic human populations had developed resistance to diseases that modern humans had never encountered. This genetic mixing may have been crucial for the success of modern humans as they adapted to new environments outside Africa. However, not all archaic human genes were beneficial in the long term. There are some that have become deleterious in our new, modern lives. One of these genes allows our blood to coagulate or clot quickly, a useful adaptation in creatures who were often injured while hunting. However, in modern people who live longer lives, this same trait of quick clotting blood can cause harmful blood clots to form in the body later in life. The timing and pattern of these encounters vary dramatically across different regions. In Europe, the period of coexistence between modern humans and Neanderthals lasted for roughly 10,000 years before Neanderthal populations finally disappeared around 40,000 years ago. In Asia, the situation was even more complex, with different Denisovan populations interacting with modern humans at different times and places over a period spanning tens of thousands of years. Some Denisovan populations may have survived much longer than previously thought. Recent archaeological evidence suggests that archaic human populations persisted in some regions of Asia until as recently as 50,000 years ago, meaning they were contemporaries of early modern human populations in the region. The end of the Great Convergence marked a fundamental turning point in human evolution. For millions of years, multiple human species had shared the planet, each adapted to different environments and ecological niches. But by 30,000 years ago, only one human species remained, Homo sapiens. The others hadn't simply died out, They had been absorbed into the modern human GENE pool through interbreeding. This process of absorption rather than replacement may explain why modern humans were so successful in colonizing new environments. Instead of having to develop new adaptations through slow biological evolution, modern humans could acquire beneficial traits from archaic human populations that had spent hundreds of thousands of years adapting to local conditions. The cultural legacy of these encounters is more difficult to trace, but may be equally important. Some researchers have suggested that certain aspects of modern human culture, from artistic traditions to spiritual beliefs, may have roots in interactions with archaic human populations. The sudden appearance of sophisticated cave art in Europe around 40,000 years ago, coinciding with the period of modern human Neanderthal contact, may not be coincidental. The Great Convergence represents one of the most significant events in human evolutionary history, the end of human species diversity and the emergence of modern humans as the sole surviving human lineage. But rather than a simple story of replacement, it reveals a complex process of interaction, interbreeding, and cultural exchange that fundamentally shaped the biology and culture of our species. The genetic legacy of these ancient encounters continues to influence human biology today. Every person of non-African ancestry carries DNA from at least one archaic human species, and in many cases, these ancient genetic variants continue to affect health, physiology, and adaptation to different environments. Perhaps more importantly, the Great Convergence demonstrates the importance of hybridization in human evolution. Rather than evolving in isolation, modern humans succeeded in part by incorporating beneficial traits from other human lineages. This pattern of genetic mixing and cultural exchange may be one of the defining characteristics of our species. The end of human species diversity also marked the beginning of a new phase in human evolution, one dominated not by biological adaptation, but by cultural innovation. With no other human species to compete with, modern humans could focus their energies on developing increasingly sophisticated technologies and social systems. As the last archaic human populations disappeared and modern humans emerged as the sole surviving human species, our ancestors stood at the threshold of the modern world. Around 40,000 years ago, equipped with the genetic legacy of multiple human lineages and revolutionary new cultural capabilities, they began the final phase of global colonization. This would be the age of art and agriculture, of cities and civilizations. The period when humans would transform from just another large mammal into the dominant force shaping life on Earth. The story of recent human evolution was about to begin. Chapter 9. Art, Agriculture, and the Birth of Civilization deep in the Lascaux Cave in southwestern France. 17,000 years ago, an artist put the finishing touches on what would become one of humanity's greatest masterpieces. By flickering torchlight, they had painted hundreds of animals across the cave walls: galloping horses, massive aurochs, and graceful deer, all rendered with a skill and artistry that would impress professional artists today. This wasn't just decoration. These paintings represented something revolutionary in the history of life on Earth: the emergence of symbolic thought, abstract representation, and aesthetic expression. For the first time, a species was creating not just for survival, but for meaning, beauty, and communication across time. The artist at Lascaux was part of a cultural explosion that began around 40,000 years ago and fundamentally transformed human society. Homo sapiens were known for their artistic talents in cave paintings and clay work. They made hooks and spears to catch fish and invented the spear thrower. Thus, it made them better hunters because they could hunt from a distance. Across the globe, from the caves of Europe to the rock shelters of Australia, humans were developing art, music, sophisticated technologies and complex social systems at an unprecedented pace. But this was just the beginning. Within a few thousand years, these same humans would invent agriculture, build the first cities, and create the foundations of modern civilization. The period between 40,000 and 10,000 years ago represents one of the most dramatic transformations in human history. This cultural explosion, sometimes called the Upper Paleolithic Revolution, saw the emergence of virtually every aspect of human culture that we recognize today. Art, music, complex tool technologies, long-distance trade, and sophisticated social organizations. The archaeological evidence for this transformation is stunning in its scope and suddenness. Beginning around 40,000 years ago, archaeological sites across Europe, Asia, and Australia begin showing evidence of behaviors that had never before appeared in the archaeological record. These include the systematic production of blade tools, the creation of personal ornaments, the development of representational art, and evidence of long-distance exchange networks spanning hundreds of kilometers. One of the most dramatic innovations was the development of sophisticated hunting technologies. Modern humans invented spear throwers, atlatls, that could propel projectiles with much greater force and accuracy than hand-thrown spears. They developed composite tools, implements made from multiple materials carefully joined together, that were far more effective than anything that had come before. But perhaps more importantly, they began hunting cooperatively on a scale never before seen. Archaeological sites from this period contain evidence of mass hunting events where dozens or even hundreds of large animals were killed in coordinated drives. These hunts required complex planning, sophisticated communication, and social coordination, involving dozens of individuals. The development of art represents perhaps the most visible aspect of this cultural revolution. Cave paintings appeared almost simultaneously across Europe around 40,000 years ago, suggesting that the capacity for artistic expression had become a fundamental part of human culture. These weren't crude scratchings, they were sophisticated works of art that demonstrate advanced understanding of proportion, perspective, and artistic technique. The artists of the Upper Paleolithic weren't just copying what they saw. They were creating symbolic representations that conveyed meaning beyond simple documentation. Many cave paintings appear to depict mythological or spiritual scenes, suggesting the development of complex belief systems and possibly the first religions. Music also emerged during this period. Archaeological sites have yielded bone flutes dating to 40,000 years ago, and evidence suggests that humans may have been creating music even earlier, using materials that don't preserve well in the archaeological record. The development of music represents another form of symbolic communication and may have played important roles in social bonding and group coordination. Perhaps most remarkably, humans began creating personal ornaments and decorative objects on an unprecedented scale. Archaeological sites from this period are filled with carved figurines, decorated tools, and jewelry made from shells, bones, and stones. These objects weren't just decorative, they were markers of individual and group identity, evidence of increasingly complex social hierarchies and possibly the first true fashion. The social implications of these cultural innovations were profound. The production of art, music, and decorative objects requires not just individual skill, but social systems that can support specialists who aren't directly involved in food production. This suggests that Upper Paleolithic societies had developed sufficient productivity and social organization to support the first non-subsistence activities. Evidence also suggests that these societies were developing increasingly sophisticated forms of social organization. Some archaeological sites show evidence of clearly defined activity area spaces, specifically designated for tool-making, food preparation, artistic production, and social gatherings. This level of spatial organization suggests complex social rules, and possibly the first formal institutions. Long-distance trade networks also emerged during this period. Raw materials for toolmaking and ornament production were often transported hundreds of kilometers from their sources, suggesting either direct long-distance travel or complex exchange networks involving multiple groups. Some materials, such as certain types of high-quality stone, shells, and amber, appear to have been traded across entire continents. As the last ice age ended around 12,000 years ago, human societies began undergoing another fundamental transformation: the development of agriculture. Beginning of agricultural communities around 12 Ca. Image is an illustration of women and men working in a field harvesting plants with small huts on stilts in the background. This wasn't a sudden invention, but rather a gradual process that occurred independently in at least 7 different regions around the world. The development of agriculture represented a fundamental shift in human relationships with the environment. Instead of simply exploiting naturally occurring resources, humans began actively managing ecosystems to increase the productivity of useful plants and animals. This required sophisticated understanding of plant and animal biology, seasonal cycles, and environmental management. The first agricultural societies appeared in the Fertile Crescent of the Middle East around 11,000 years ago, where humans began cultivating wheat, barley, and legumes while domesticating sheep, goats, and cattle. Similar developments occurred independently in China, rice and millet; Mesoamerica, maize, beans, and squash; the Andes, potatoes and quinoa; Eastern North America, squash and sunflowers; New Guinea, bananas and taro; and Africa, yams and African rice. The development of agriculture had profound consequences for human society. Agricultural communities could support much larger populations than hunter-gatherer societies, leading to rapid population growth. They also enabled food storage, which allowed communities to survive seasonal shortages and support individuals who weren't directly involved in food production. Perhaps most importantly, agriculture enabled the accumulation of surplus resources, which became the foundation for social stratification, specialized occupations, and eventually, complex civilizations. For the first time in human history, some individuals could accumulate significantly more resources than others, leading to the emergence of social classes and political hierarchies. The first cities began appearing around 9,000 years ago in Mesopotamia, followed by urban centers in the Indus Valley, Egypt, China, and Mesoamerica. These early cities were marvels of social organization, supporting populations of tens of thousands of individuals, engaged in dozens of specialized occupations. The development of writing systems around 5,000 years ago marked another crucial milestone. Writing enabled the storage and transmission of complex information across time and space in ways that had never before been possible. It allowed for the development of formal laws, complex administrative systems, and the preservation of knowledge across generations. But perhaps the most significant development of this period was the emergence of what we might call cumulative cultural evolution. Unlike biological evolution, which operates through random mutations and natural selection over many generations, cultural evolution could operate much more rapidly through intentional innovation and directed learning. Humans became capable of deliberately improving their technologies, social systems, and understanding of the world through experimentation and innovation. This created a feedback loop where cultural innovations enabled further innovations, leading to an accelerating pace of change that continues to this day. The genetic implications of these cultural changes were also significant. As humans developed agriculture and began living in larger, more permanent settlements, they were exposed to new diseases and environmental pressures. Natural selection began favoring genetic variants that provided resistance to crowd diseases. ability to digest new foods, particularly dairy products, and adaptation to new dietary and lifestyle patterns. Some of the most rapid evolutionary changes in recent human history occurred during this period. The evolution of lactose tolerance in several human populations, genetic adaptations to high-starch diets, and resistance to infectious diseases all occurred within the last 10,000 years recent. Enough that these adaptations are still distributed unevenly across different human populations. The cultural explosion of the late Paleolithic and the subsequent development of agriculture represent the most rapid and dramatic transformation in human evolutionary history. In the span of just 30,000 years, a blink of an eye in evolutionary terms, humans went from small bands of hunter-gatherers to complex civilizations capable of monumental architecture, sophisticated art, and detailed written records. This transformation demonstrates the unique power of cultural evolution in human development. While biological evolution enabled the basic cognitive capacities necessary for culture, it was cultural evolution that allowed humans to transcend the limitations of their biology and become the dominant force shaping life on Earth. The development of agriculture also marked the beginning of what some scientists call the Anthropocene, the geological epoch in which human activities began to significantly alter Earth's environment and climate. From this point forward, human cultural evolution would increasingly shape not just human society, but the entire planet. Perhaps most remarkably, this entire transformation occurred without any significant biological evolution. The humans who built the first cities and invented writing were genetically almost identical to the hunter-gatherers who created the cave paintings at Lascaux. This demonstrates the incredible flexibility of human culture and its power to generate new forms of organization and behavior. As human civilizations grew in complexity and spread across the globe, they were setting the stage for an entirely new phase of human evolution. For millions of years, human evolution had been driven primarily by natural selection and adaptation to environmental challenges. But as humans gained increasing control over their environment through technology and social organization, new evolutionary pressures began to emerge. The story of recent and ongoing human evolution would be shaped not by caves and ice ages, but by cities and agriculture, global trade and communication, and ultimately, by humans' own choices about their future development. Chapter 10. Human Evolution and the Age of Civilization in a Laboratory in Boston. A scientist pipettes a sample of blood into a genetic sequencer. The sample comes from a Tibetan Highlander who can work comfortably at altitudes where most people would collapse from altitude sickness. Thousands of miles away, another researcher collects saliva from a Finnish dairy farmer whose ancestors evolved the ability to digest milk as adults. A pulse from a Finnish dairy farmer whose ancestors evolved the ability to digest milk as adults. A pexager collects saliva from a Festeris farmer for a trait that didn't exist 10,000 years ago. Meanwhile, in London, a team analyzes the genomes of people whose ancestors survived the Black Death, searching for genetic variants that provided resistance to plague. These modern investigations reveal a startling truth. Human evolution didn't stop when we invented agriculture and built cities. If anything, it accelerated. Since the development of agriculture 10,000 years ago, humans have evolved at least 100 times faster than any previous period in our species' history. We are not the same species that built the first cities in Mesopotamia. In fact, genetic studies revealed that as much evolutionary change has occurred in the last 10,000 years as in the previous 300,000 years of modern human existence. This recent evolution has been driven not by the traditional forces of climate and predation, but by the new environments that humans themselves have created. dense cities, agricultural diets, infectious diseases, and global trade networks. The last 10,000 years of human evolution represent a unique period in the history of life on Earth. The first time a species has significantly evolved in response to environments of its own creation. As humans transition from hunter-gatherer societies to agricultural civilizations, they created entirely new selective pressures that drove rapid evolutionary changes across multiple human populations. One of the most dramatic examples of recent human evolution is the development of lactose tolerance, the ability to digest milk as an adult. All mammals, including early humans, lose the ability to produce lactase, the enzyme that breaks down lactose after weaning. This makes perfect biological sense. Why continue producing an enzyme that's only needed for processing milk when milk is no longer part of the diet? But around 7,500 years ago, something remarkable happened in several human populations that had begun domesticating cattle, sheep, and goats. Genetic mutations arose that kept the lactase enzyme active throughout adulthood, allowing these populations to digest fresh milk and dairy products. This provided a significant nutritional advantage, especially in northern latitudes where vitamin D was scarce and the calcium in dairy products was particularly valuable. The lactose tolerance mutation didn't just arise once, it evolved independently in at least 7 different human populations across Europe, Africa, and Asia. This is a textbook example of convergent evolution, where the same trait evolves multiple times in response to similar environmental pressures. Today, lactose tolerance is present in over 90% of adults in some Scandinavian populations, while remaining virtually absent in East Asian and many African populations. Even more remarkable is the story of high-altitude adaptation in human populations. When humans first colonized the high-altitude regions of Tibet, the Andes, and Ethiopia, they faced severe physiological challenges. At altitudes above 12,000 feet, the reduced oxygen availability causes most people to suffer from altitude sickness, reduced physical performance, and complications during pregnancy and childbirth. Yet within just a few thousand years, populations in these regions evolved sophisticated biological adaptations to high-altitude life. Tibetans evolved changes in hemoglobin regulation that prevent the overproduction of red blood cells that causes problems in most high-altitude visitors. Andean populations developed increased lung capacity and enhanced oxygen-carrying capacity. Ethiopian highlanders evolved yet another solution involving improved oxygen utilization at the cellular level. Perhaps most remarkably, genetic analysis has revealed that some high-altitude adaptations in Tibetans were inherited from Denisovans, the archaic human population we discussed earlier. The EPA's one gene variant that helps Tibetans thrive at high altitude was acquired through interbreeding with Denisovan populations tens of thousands of years ago, then favored by natural selection as modern humans colonized the Tibetan plateau. The development of agriculture also drove rapid evolution in genes related to diet and nutrition. The AMY1 gene, which produces an enzyme that helps digest starchy foods, shows dramatic variation between different human populations. Agricultural populations that relied heavily on starchy crops like rice, wheat, and potatoes evolved multiple copies of this gene, allowing them to more efficiently extract nutrition from their carbohydrate-rich diets. Similarly, populations that relied heavily on fish developed genetic adaptations for processing omega-3 fatty acids. Inuit populations, who traditionally obtain most of their calories from marine mammals, evolved genetic variants that allow them to thrive on extremely high-fat diets that would be problematic for most other human populations. Disease resistance has been another major driver of recent human evolution. As humans began living in large, dense settlements and domesticating animals, they were exposed to new infectious diseases that had never before affected human populations. Diseases like malaria, tuberculosis, plague, and smallpox became major. Selective forces, driving the evolution of resistance mechanisms in affected populations. The relationship between malaria and sickle cell anemia provides a classic example of this process. The genetic mutation that causes sickle cell anemia is harmful when present in 2 copies, causing severe health problems and often death. But when present in just 1 copy, it provides significant protection against malaria. In regions where malaria is common, natural selection has maintained the sickle cell mutation at relatively high frequencies because the protection it provides against malaria outweighs its harmful effects. Similar patterns of disease-driven evolution can be seen with other conditions. Tay-Sachs disease, cystic fibrosis, and thalassemia all appear to provide protection against specific infectious diseases when present in single copies, explaining why these otherwise harmful mutations persist in certain populations. The urban environments created by human civilization have also become new evolutionary pressures. Studies of modern urban populations have found evidence of ongoing evolution in response to air pollution, noise pollution, and the unique social stresses of city life. Some urban populations show genetic changes related to inflammation and stress, response that may represent adaptations to city living. Even more intriguingly, recent studies have found evidence that human evolution may be responding to cultural and social changes. The Flynn effect, the observation that IQ scores have been increasing over the past century, may reflect evolutionary changes in cognitive abilities in response to increasingly complex social and technological environments. Genetic studies have also revealed ongoing evolution in human reproductive biology. Changes in the timing of puberty, fertility rates, and even preferences for certain physical characteristics appear to be evolving in response to modern social and environmental conditions. Perhaps most dramatically, advances in genetic technology are beginning to give humans direct control over their own evolutionary future. Gene therapy techniques can now correct genetic disorders in individual patients, while emerging technologies like CRISPR gene editing hold the potential for making heritable changes to the human genome. These technological capabilities raise profound questions about the future of human evolution. For the first time in the history of life on Earth, a species has gained the ability to deliberately direct its own evolutionary development. This represents a fundamental shift from natural selection to what might be called artificial selection, or directed evolution. The implications are staggering. Humans may soon be able to eliminate genetic diseases, enhance cognitive abilities, extend lifespan, and possibly even add entirely new capabilities to the human genome. Some researchers have suggested that we may be approaching the end of natural human evolution and the beginning of a new phase where human development is guided by conscious choice rather than environmental pressures. But this technological control over evolution also raises ethical and practical challenges. Who gets to decide which traits are enhanced or eliminated? How do we ensure that genetic modifications benefit all of humanity rather than increasing inequality? And what are the long-term consequences of making permanent changes to the human genome? Recent advances in understanding human genetics have also revealed the incredible complexity of human evolution. Rather than being driven by single genes with large effects, most recent human evolution appears to involve subtle changes in many genes, each with small individual effects but significant cumulative impacts. This polygenic nature of recent evolution means that human populations around the world have diverged not just in obvious traits like skin color and body build, but in thousands of subtle genetic variants affecting everything from disease, resistance to cognitive abilities, to personality traits. Modern human populations represent a vast natural experiment in adaptation to different environments and cultural conditions. Global migration and intermarriage are now beginning to reverse some of this population-level divergence, creating new combinations of genetic variants and potentially new evolutionary trajectories. The genetic mixing that characterizes modern global populations may be creating hybrid vigor effects that enhance human adaptability and resilience. Climate change and environmental degradation are also creating new evolutionary pressures that may shape future human development. Rising temperatures, changing disease patterns, increased ultraviolet radiation, and environmental pollution are all potentially significant selective forces that could drive continued human evolution. Perhaps most intriguingly, the digital revolution and the rise of artificial intelligence are creating entirely new environments that may influence human evolution. Some researchers have suggested that the cognitive demands of modern technological society may be driving continued evolution of human intelligence and information processing abilities. Social media, virtual reality, and constant connectivity are changing how humans interact, communicate, and process information in ways that may have evolutionary consequences. The ability to rapidly filter and process large amounts of information, multitask effectively, and maintain social connections across digital networks may become increasingly important survival skills. The story of recent human evolution reveals that our species has not stopped evolving. Instead, we've become the primary driver of our own evolutionary development. The environments we create through technology, agriculture, medicine, and social organization are now the main forces shaping human biological development. This represents a fundamental transition in the history of life on Earth. For billions of years, evolution was driven by environmental pressures, largely beyond the control of individual organisms. But humans have now gained sufficient control over their environment and increasingly over their own genetics to direct their evolutionary future. The challenge moving forward will be to use this unprecedented power wisely. The genetic diversity that has accumulated in human populations over tens of thousands of years represents a valuable resource for adapting to future challenges. Maintaining this diversity while enhancing human capabilities will require careful consideration of the long-term consequences of our choices. Perhaps most importantly, the story of recent human evolution demonstrates that we are still very much part of the natural world, even as we increasingly reshape that world to meet our needs. Understanding how evolution continues to operate in human populations will be crucial for addressing challenges, ranging from emerging diseases to climate change to the ethical implications of genetic enhancement technologies. As we stand at the threshold of an era where humans can directly control their own genetic destiny, the story of human evolution enters its most uncertain and potentially transformative chapter. The same species that evolved from tree-dwelling apes 7 million years ago now possesses technologies that could fundamentally alter the trajectory of life on Earth. The final chapter of our evolutionary story is not yet written indeed. We are now the authors of that story ourselves. The question is not whether humans will continue to evolve, but how we will choose to direct that evolution in the centuries and millennia to come. As we reach the end of this epic journey through 7 million years of human evolution, we're left with a profound realization: the story isn't over. In fact, we may just be at the beginning. From that first Australopith who stepped down from the trees, to the modern scientists who can edit genes with molecular precision, human evolution has been a story of continuous transformation, adaptation, and transcendence. We've survived ice ages and volcanic winters, develop technologies that extend our capabilities far beyond our biological limitations, and spread to every corner of the planet. But perhaps the most remarkable aspect of our evolutionary story is its acceleration. The same species that took millions of years to develop stone tools has, in just the last few centuries, split the atom, mapped the human genome, and begun to explore space. Cultural evolution has not only supplemented biological evolution, it has largely superseded it as the primary driver of human development. Today, as we grapple with climate change, emerging diseases, artificial intelligence, and genetic engineering, we face challenges that would have been incomprehensible to our ancestors. Yet we face them with brains that are essentially identical to those of the humans who painted caves at Lascaux 17,000 years ago. Our biology hasn't changed, but our capabilities have expanded exponentially through the power of cumulative culture. The genetic legacy of our evolutionary journey lives on in each of us. Every person carries DNA from the earliest modern humans who left Africa, from the Neanderthals who survived the European ice ages, and from the mysterious DENISOVANS who conquered the heights of Asia. We are living libraries of human evolutionary history, walking monuments to the epic journey that brought us to this moment. Looking forward, we stand at an unprecedented threshold. For the first time in the history of life on Earth, a species has gained the power to consciously direct its own evolution. The choices we make in the coming decades about genetic engineering, artificial intelligence, space colonization, and environmental management will shape not just our immediate future, but the entire trajectory of human development for millennia to come. The question that began our journey, how did we get here, has been answered through the patient work of scientists who piece together our past from fragments of bone and DNA. But an even more profound question now confronts us. Where do we go from here? The next chapter of human evolution is ours to write. The same creativity, adaptability, and collaborative spirit that carried our ancestors through ice ages and across continents will guide us as we venture into an uncertain but extraordinary future. The journey that began 7 million years ago in the forests of Africa continues, and we are all part of it.